All right, everyone. Welcome to the theory seminar. I'm Suresh. This is my first ever theory seminar, so I'm Suresh Venkat. Very happy to introduce Manon Revel, coming from the Berkman Klein Center at Harvard. Manon did a PhD at MIT in the department. That's an interesting name for the department: Social Engineering Systems and Statistics. Is it all of them together?
It's even more obscure. This is the name of the PhD program.
Okay.
The department
inside
is
IDSS.
Yes, exactly.
Oh, okay. So there's the Institute for Data and whatever.
Yeah, Institute for Data Systems and Society.
And then there's PhDs in
yes,
the specific. Okay,
exactly.
Great. And as you can tell, Manon has sort of a wide range of interests. You describe yourself as a social choice theorist, which I'm sure you'll explain what that means. But she's interested in AI governance, content moderation, philosophical underpinnings, AI alignment. So I think it will be a great talk. So thank you for coming.
Thank you very much. And thank you very much for the introduction and to Ritie for the invitation. I'm super excited to get to share some of my research. And so, indeed, I just moved to Harvard a few months ago, and I've been super interested in thinking about the intersection of technology and policy, in particular in the context of social media governance and generative AI governance. What I would talk about here is fairly different. So we can move on to these other topics, but right now I'll be really focused on the main part of my dissertation, which was in social choice theory. How many of you know the term even social choice theory? A few. So social choice theory is the name of a mathematical field that was created in the 1800s to study how humans make decisions and how we can aggregate different preferences into an output that then you can use in real world decision making. Do you know ensemble learning? Is this something that more of you have heard of? So a lot of the work in ensemble learning has been built on some of the assumptions and some of the modeling of social choice theory. The ensemble learning part is how do you make decisions with models. The social theory part is how you make decisions with humans. And so your classifiers are basically just all of us in this room and actually humans. And so I will present a lot of different pieces of my work that I've done in different fields. So I want to first acknowledge all of my collaborators, and then you're going to see how these different aspects pieces together. So this has been the professors I worked with during my PhD on my committee. Alijat Babai, my PhD advisor, Manzur Dahel and Adam Berinsky are all at MIT, and Ariel Procaccia is a CS social choice theorist at Harvard, and Eric Berbaum is a philosopher at Harvard University. And also want to acknowledge my co-authors on the different works I will be presenting. Danielle Halpern, a CS PhD student at Harvard. Elhanan Mosel, a mathematician at MIT, Joe Halpern, computer scientist at Harvard, and Tao Lin, also PhD student in computer science at Harvard. So the question I've been super interested in during my PhD is this question of governance that I define as accommodating a potentially irreconcilable plurality of views. And I will nudge you to think about governance in the particular context of representative democracy, which is the exercise that we all make when we are going to the booth and we have to vote for people that represent us in the Congress. I am sure that as citizens yourself, you've heard about a lot of the issues that we're having with democracies or representative democracies. Just a few polls, and we have a lot of different indexes about not only, this one is US-centric, but we have a lot of different indexes about how democracy has been in what some people call decline or recession, throughout the world. This is a poll from 2022 about the percentage of people that trust the U.S. Supreme Court or the U.S. Congress, and we are, obviously in a pretty steep decline. This is definitely the most pessimistic poll I found. So I don't know how representative it is on its own, but we had in 2022 this poll showing 7% of the Americans expressing trust in their Congress, which is definitely not something that you'd want to have from your institutions. But on the positive side, there have also been a lot of appetite in democracies worldwide to think outside the box in terms of how we can design institutions for democracies. So a few examples here. The first optimist note is this idea that most people across democracies still believe that representative democracy is a good way to be governing, and many publics believe that we can reform and that we should reform the different political systems. And a lot of different areas have been explored in how we can make these changes in democracy. I have a few that I want to name here. So I don't know if you've ever heard of these of ranked choice voting. That may be a term that you've heard. So in the 2022 midterms, there were a poll that was asking whether Nevada should change its political system, or at least during the election, so that you would have both an open primary during pre-elections, and then you would aggregate voters' preferences through ranked choice voting. This has been one of the most active area of electoral reforms. Has been changing the form of the ballots, and so not having just one person that you put you're not just putting the name of one person, but you're actually ranking the different candidates that you're having, and you use different algorithms to aggregate the rankings and decide who's the winner. Open primaries is another idea to decrease polarization and having all of the candidates being on the same ballot. A lot of questions about the Electoral College. This is again particularly US-centric. Also questions about the size of the Congress, which is something else I worked in other parts of my research that I'm not presenting today. But what should be the parameters that we should be thinking about when we think about enlarging or reducing the size of the Congress? And we also have math models to appreciate or answer parts of these questions. And lastly, maybe completely changing the way in which we do democracy. And another proposal I want to mention, and I'll come back to it afterwards, is this idea of not electing candidates, but actually selecting people at random from a population. So this is the idea of sortition or lotocracy, the idea of governing by lot. And this piece here is from an interview the New Yorker did of Hélène Landemore, a political philosopher who's done really great work on this particular question of changing political representation through not moving away from election with sortition. And so along this kind of line, I'll share another model or another thing that we could be thinking about in terms of representation that's definitely outside of the box, and I'll get into the mathematical formulation of it before going back into how we can make a concrete change and concrete impact on the problem with representative democracy that I was mentioning. And the key word that I have in mind, and that's been really the driver of all of my dissertation, has been this idea of legitimacy, that I will define as how representative democracy can lead to a grounded acceptation that the process matters more than my opinion. And if you think about governance, there is really something about this, that we might have very different opinions, and at the end of the day we need to aggregate these opinions into just one outcome. And there might be some violence in that my opinion might not percolate until the final decision. And the idea of legitimacy would be that I will surrender my opinion to the process, and I will accept that the process is ruling over my particular opinion. So it's how I will be thinking about legitimacy. And there's a ton of work in political philosophy about how we should define legitimacy, how it has been exercised throughout history. If you're interested in the philosophy part, on the empirical perspective, Max Weber has been doing some of the most well-known work on thinking about what creates political legitimacy. And you still have very constantly work being done about redefining and trying to think about a model for legitimacy that would allow us to design better democracies. It's a bit the same thing with alignment, that AI alignment, or like a lot of the auditing of algorithms, where to be able to design auditing or governance, we need to have the right metrics to evaluate them, but we don't really know how to define the metric. And it's kind of the same issue here, where we need to have a metric that's legitimacy, but it's a moving target because we're still defining exactly how it should be. But still, there's much more work done on the concept of legitimacy than on the right standards for what makes AI responsible or ethical. And actually, I want to use two particular legs of legitimacy that are this idea of procedural legitimacy and epistemic legitimacy, which are kind of the two dimensions on which you can want to decompose your signal when you're looking at what makes that your system is being legitimate. The idea of the epistemic legitimacy is that you're thinking that the outcome of your representative democracy is good. So it's the idea of having an epistemic value being assigned to your representative democracy, and that it is leading to good outcomes, this idea of rightness or goodness of the outcome. And then the procedural aspect has nothing to do with the outcome. It's all related to how the procedure is performing. Do you think that the procedure has intrinsic guarantees or intrinsic features that make it legitimate? And I want to talk a bit about both, but I'll focus primarily on the two first chapters, which are on the epistemic aspect. And you might start guessing it with the idea of having a standard of rightness or correctness is a really great kind of opening for mathematicians or computer scientists or social choice theorists to think about modeling democracy in the epistemic sense. So the two first chapters are really on the epistemic dimension. And if we have time, I'd love to share some of my philosophy work as well, which is the third aspect. which is, as I said, distinct in that it's looking at legitimacy from this procedural perspective. So the main part is this part 1. It's a discussion about the epistemic dimension of governance, and in particular in this context of electing representatives. And I'm relying on the work of Nicolas de Condorcet, we think of him as the founder of social choice theory. I think if we're fair, we should actually attribute the birth of the field to a Catalan philosopher, Ramon during the Middle Age, and he's kind of worked on very similar things than Condorcet, but Condorcet really formalized it within probability theory. He's also independently a fantastic thinker who's been really involved in thinking and combating slavery and combating for women's rights during the French Revolution. And so I'm talking about someone in the 18th century, which was he's been very influential and still inspiring for many of us still today. And he laid down this epistemic framework, which is a mathematical formulation for decision making in the context of us trying to track a good outcome. And it's very simple. As you look at n agents, so it's your classifiers in the ensemble learning vocabulary. Here it's n voters, it's just us, that are independently voting on an outcome and it's a binary outcome. And you assume that one of the outcome is the ground truth. So with that loss of generality, we will denote by 0 the wrong answer and 1 the right answer. And the whole name of the game in this system is to identify the correct outcome. And all of us have some probability, which we can think of as our expertise to identify this correct outcome. So everyone is just parameterized by a probability pi, your expertise of finding the correct outcome. Probability that your vote is 1, your vote is correct. And just with this very simple formulation, you can start seeing things that were really counterintuitive in the 18th century that might sound to you more intuitive now with the kind of modern probabilistic toolkit that you're having. But looking at this toy example here, you can look at this tiny society of 3 people with respective probability of being correct, 80%, 80%, 90%. And you can start checking what is the performance of different decision rules. And I'm going to talk about 2 rules right now. One, majority, which is just the outcome that has most votes wins. And the other one as epistocracy, which is the rule of the expert, the rule of the most performant agent. And so if you look at the majority here, the probability for your majority to be correct is exactly the probability that at least 2 of the agents are correct. And this happens if either the 3 persons are all correct or 2 of them are correct and 1 is incorrect. So you have these 4 different events, and the probability that the majority is correct is the sum of the probability of these events. Because the votes are independent, the probability that either of these events is true is just the product of the probability that the individual voters behave according to the parameterization. You can just do the computation, it's 92%. And what you directly see is that this is higher than the probability that your top expert is correct. And you have this thing that people have later coined this idea of wisdom of crowds or collective intelligence, which is that when you aggregate together signals that are not perfect individually, you can actually get better results by aggregating a bunch of noisy signals. And this comes from a result that Condorcet showed in 1785 that we call Condorcet-Jury theorem. It's a direct consequence of the law of large number. And it says that if you have now a society and the average expertise within your society, so the average PI is strictly above a half, then the probability that your majority is correct as n goes to infinity is going to tend to 1. And you can think of it as, this is literally you look at the empirical average, your xi over n, and you know that this will converge towards its mean. And if the mean is above a half, then eventually all of the weight of your sample mean will be above a half. So the probability that it is above a half would just go towards 1 as a consequence of this. The exact reverse scenario is true as well. If the average expertise is below a half, then the majority is going to be incorrect with probability 1 as n goes to infinity. And you have this kind of like very discontinuous or like contrasting pattern, or saying that the average information of your group is kind of governing the collective intelligence versus the collective confusion of your society. So the thing that when I discovered all of this work, I just found it just cool. I did all of my undergrad in math, and I was always wondering how it could be relevant to society, and I was learning a lot about the different fields, and there are so many ways in which math is. And I was interested in these questions about democracy and how we can model human behavior. And I found this framework very simple and very elegant in a way that made me think about the following question, which is all of what Condorcet has been studying is what happens when you aggregate the information that we have about a particular question. So I was telling you that my PI parameterizes the probability that I make a right decision according to information I have about a particular topic, the topic that's at stake. And I was wondering how we could leverage the same idea by not only using the information that we have about a topic, but also the information that we have about one another about this topic. So, concretely, I care a lot about climate change and I have no knowledge about climate science, but I have a lot of my friends that have this knowledge. And is there anything that we can make about this information of the people that I know and the people that I trust? Could we use this to improve decision making? And this is basically the idea behind a system called liquid democracy that has been formally defined in 2000 by computer scientist Brian Ford, but you find traces of it before in a politician. James Miller talked about it in '69. And then the first person who actually talks about it in the terms that we know is Lewis Carroll, who talks about a system that's basically liquid democracy, though he doesn't describe it as liquid democracy. So the idea of liquid democracy, high level, is really, can we use information that is embedded in the network about what we know about one another to make better decisions? And concretely how it works is that you have, let's say that this is your network, this is us in this room, and at the time of the decision, either we nominate a representative or we vote. And so you can either use the information that you have about the issue or use the information that you have about the others. And so you have this kind of delegation graphs that appear with the particular feature that delegation graphs are transitive. And what I mean by this is that if I delegate my vote to someone who in turn delegate their vote to someone else, then my vote is basically passed along this last person. And the way you look at the vote is, you do this to choose your representative, and then the representative vote through a weighted majority. And why do I say weighted? Well, because for the system to be representative, we want my vote is not lost, and so my vote is counted towards the final outcome by weighting the power of my representative. So the blue person here has a weight of 1 because no one delegated to them, and they're just representing themselves, so it's weight of 1. The orange person gets 1 delegation, so has a weight of 2 to represent themselves and their delegatee. And here the yellow person has a weight of 3 because of the transitive pattern of delegation. And when you delegate, your weight is 0. You nominate someone to represent you. And so when I studied my PhD, the literature was at a point where people yes?
How do you eliminate cycles?
Yeah, that's a great question. So in practice, the way it's done is cycles are ignored, which poses a big procedural questions about, do I care if I'm in a cycle and I'm just ignored in the outcome? In our math analysis, we assume that people in a cycle are wrong, so that the analysis, the result that we have is robust to the existence of cycle, but it's definitely one of the two, I think, main pragmatic questions when we think about implementing liquid democracy that matters. And I think Professor Sheng worked on this question about distortion. I'm making a little analogy here in that the point where the literature were when I studied my PhD was thinking that we can create this very worst case scenario where in our case liquid democracy collapses because the votes end up in the hands of a few people, and even if you end up in an epistocratic setup, the one I was showing you before where only a few people have a lot of power, then you actually you're not doing any good because you just concentrated the power in the hands of too few. And I think when you were working on distortion, there was the same idea of we have this worst case scenario of distortion if you look at very pathological ways in which representatives are being sampled in a metric space. And a natural following question is, but how likely is this if you look at probabilistic sampling of either a representative in the context of distortion or in our case the idea of delegation. So the question that I've been asking is how likely is it that we get into these bad case scenarios? And if you look at the probabilistic understanding, if you have a probabilistic understanding of the world, how likely it is that liquid democracy works well versus not well. So this was the intro for how we do epistemic democracy in math, and I want to get now into the details of analyzing liquid democracy with the question that I think now you'll you got, which is, can we improve this idea of epistemic representation using what we know about who knows, and not just using what we know about a particular topic.
So does that mean that you will then answer the question of what is the mechanism by which I decide to delegate?
Yeah, indirectly.
Okay.
Which is, I think in 2 slides, it's exactly what I'm getting. The first slide I want to show is why this is not completely trivial. So if you look at the probability here of the sum of the wi xi, before we had just the sum of the xi's, which is what happened with majority, and here we have our weighted majority, which is what our representatives do once after they've been selected with delegations. And so what we care about is, how does this probability evolves with the delegation graphs. And so let's take another example with just 5 people, and we look at the probability that here this delegation graph is correct. It's 77%, no one delegated, so this exactly coincides with majority. Now, maybe intuitively, if you have the 2 50% agents that delegate upward to people that are more expert than them, then you increase the probability of correctness to 85%. But now, perhaps counterintuitively, if one of the more expert person, the 70% delegates downward to a 50%, you're still better off than if no one had delegated. Just, maybe a little odd, or not exactly what we would have thought in terms of, oh, maybe we just need to have the better people voting. Now, perhaps intuitively, if delegation goes downward, in that the 60 and 70% delegate to someone who's worse than them, then you decrease the probability of correctness compared to the majority voting case. But now, perhaps counterintuitively, you can have a case where people delegate to others more expert than them, but you still decrease the probability of correctness to 70%. And what I want you to get across with this is that there is actually a pretty intriguing, mathematically, entanglement between the probability of correctness and the weight that people gather after delegations. So now going into how we precisely model it and getting to the question of how people make these decisions. So the first thing the first thing is that we assume that we have a complete graph, so you can delegate to anyone. So it's like a community of people that know each other well, and then you sample everyone's expertise based on some distribution D that represents your society. So this is pretty standard how you'd model society with some continuous distribution of expertise, like uniform or whatever you want. Now we have 3 steps that matter in this analysis. The first one is that we need to know something about the local delegation behavior, so how people delegate, and we need to parameterize it to get some traction on how we model liquid democracy. Then these local delegation behaviors, they map onto macro features of the delegation graph. So you have a relationship between my local decision and the macro graph after delegation. And then the macro features of your graph impact the result, which is the probability of correctness of liquid democracy. And so basically what I do now for just the rest of the chapter is go through how we go from modeling local behaviors to how do the local behaviors map onto macro features and how the macro features map onto the benchmarks. Though, sorry, I will do it in the reverse direction. So I will start telling you what are we after, what do we want, how do we define liquid democracy being performant, and then what do we need in terms of macro features for the benchmarks to be met, and then how do we define the local delegation behavior, and when do we know that the local delegation behavior maps the macro features that in turn would be mapped onto good results and benchmark. I hope it's not too confusing. So first, what is the benchmark? What I mean by this is how do we define that liquid democracy is working well? We are using 2 benchmarks in the literature. I'll define them and then I'll give you, the intuitive just thinking about them. So the first benchmark is this idea of positive gain, which is that you want that there exists a distribution such that the gain of liquid democracy is close to 1 for large instances with high probability. And the gain is the difference between the performance of liquid democracy and majority voting. So what you want is that in some cases where majority voting is doing very bad, you want liquid democracy to be doing really well. So this is that you want that in some cases it's much better to use this representative system than to use direct voting. Yes?
Does this distribution here mean over both the knowledges and the delegation?
Great questions. No, this is the distribution I'm referring to here is just the distribution of competence. We'll define in a second But it's a great question because that will induce a distribution over all of the possible graphs that hopefully will become clear in a second. And so this is, we want in some cases that this is really good, and we want that in all cases it's not bad. This is kind of the intuitive understanding. So we have also this do no harm idea, which is that for every single distribution, we want that the loss of liquid democracy, which is the difference between the performance of majority voting and liquid democracy, it's just the negative gain. We want this to get arbitrarily small for largeness instances, which means that when liquid democracy converges to 1, when it's accurate, when majority goes to 1, we also want liquid democracy to go to 1. And in the cases where majority voting is bad, in fact, liquid democracy could do whatever, it doesn't matter per the perspective of the do no harm. But so, these are the benchmarks in the literature. The way I really want you to think about this is that all of these benchmarks are about the convergence of a weighted majority. It's about how well is your weighting majority concentrating around its mean, basically, and that's the whole name of the game when you look at the benchmark part. And one way to think about this is to look in the literature at the sufficient and necessary conditions that we have about the convergence of a weighted majority. And so, in particular, Elhan Al-Mosel and Gil Kalai in 2004 and 2006 have been working on this law of large number for weighted majority, which gives you, depending on the context, sufficient or necessary and sufficient conditions that guarantee that your weighted majority is concentrating around its mean. And the conditions that you need to be looking at is something that's called the influence of a voter, which has to do with the covariance between my vote and the outcome of the rule. And the sufficient conditions look something like the weighted sum of the influence of voters has to be sublinear for the weighted majority to work well. The issue is that it's super hard to actually compute this influence. So it's really hard to map these very tight conditions onto the macro behaviors of our graph. So what we've been after is to find non-trivial sufficient conditions that can actually be exploited in our particular context, which is now the point of the sufficient macro conditions. So when you look at your delegation graph, what do you want for liquid democracy to work well? And what we proved is that you want that it is sufficient if that with high probability, no voter has a linear weight, so that the max weight that someone aggregates after the transitive delegation is sublinear, and the average competence post-delegation increases by some small margin, then liquid democracy will perform well. So you can think of it as if you have these conditions being satisfied, and in fact, the second one is related to the benchmarks. In the second one, you could say that you want the expected expertise post-delegation to be above a half, and the max weight to be sublinear, and this would be sufficient for the probability of a weighted majority to converge. And so the parts, what you would of course expect as sufficient conditions is you want that the number of people that are being representative increases with n. If you have a cap on this, then obviously you won't have convergence. But this itself is not sufficient. If I get like a fraction of the votes, and then you still have and everyone else vote themselves, we will still have an increase in the number of representatives, and then you need to have a very careful analysis based on the relative my expertise versus the expertise of everyone else to actually understand whether you have convergence.
Just to clarify, the pre-delegation average competence is already assumed to be strictly 1.5.
No, so they are kind of, in this perspective, not at all. So what you need is you just want that post-delegation you increase by some small amount. What I was saying is that if you want to, and this is how we map the macro conditions onto the benchmarks, and the benchmarks have to do with the comparisons between liquid and majority voting. But you could generalize this into a result for the convergence of weighted majority, in which case you just care about the average expertise post-delegation to be above a half. Yes?
Why does this term correspond to increase in competence?
Oh yeah, sorry.
Yeah.
So you could replace the expertise of xi by the pi. And so this is the sum of wi pi minus the sum of the pi over n, if you change the n from the other side, being greater than 2 alpha.
And alpha is?
It's like, yeah, there exists a alpha. If there exists a alpha such as this is true, then we have the guarantees on the benchmark. And if you just remove that part, and you just change the right-hand side by a half, you transform our result, not in the case of the literature benchmark, but in the case of looking at weighted majority in general.
So, I'm trying, and I don't want to, please tell me to wait till you're done, that's fine too, but that my intuition is like firing off like this doesn't make any sense to me, because if my initial confidence was whatever, and it increases to, I don't know, 0.01, like a bunch of voters don't know anything, and even after delegation they don't know anything, how will this suddenly make liquid democracy perform well? So something wrong with my intuition here, so I'm just
No, so I think it's exactly to the question of what do you mean by liquid democracy performing well?
Yeah.
And what I was explaining in the benchmark is that the
It's relative to majority.
well, right. So you have one of the which maybe I created confusion by describing this as the benchmark level and the intuition level. The benchmark level is really as compared to direct majority.
Will suck as well, so it's
Yeah, exactly.
Yeah.
But then we have this positive gain, which means that for this to be, for our theory to work, or what we want the theory to achieve is that in some cases liquid democracy is actually much better. So in the case that exactly what you said. So in some cases if both are bad, but you want to have this cases where one gets really good and the other one gets really bad. And so this I think like goes over a lot of the thing I was just saying, but basically what we are after is, and this also gets to the question of here comparing liquid democracy with majority voting. Here really what we're looking at is just the concentration of different random variables around their means, and it's very simple when we look at at majority voting, because we know it's like all of the xi's are bounded and like it's just like Hofding inequality, the simple ones. In the case of liquid democracy, it's harder because the xi's now are not bounded. It's like wi xi's and the wi's are not bounded, so we just need to do a little bit more work, and Chebyshev is sufficient, so the variance itself won't be bounded, but it is sufficiently bounded to show that liquid democracy would be close to its mean as long as the max weight is sublinear. So this is like just concentration of random variables around their mean, and finding sufficient conditions on weighted majority for this to be true. Now to the local delegation aspect. So I told you, what we want liquid democracy to in all cases be no worse than majority, and in some cases be much better. And then I told you, how do we do this? Well, we want that no one gets more than a sublinear number of votes. And so how do we get there? Well, we need to see how people actually delegate locally. And so we model delegation in the following way. And I think it's something I say typically at the end of the slides, but I want to say up front here. We're not saying that this is like prescriptive. We're not saying people are doing this like cognitive computation of probabilities and then outputting this behavior. We're saying it's like a macro way of abstracting how delegation works. So it's like just an abstraction, like a modeling of what's happening, not as like people making the calculation, but just a way of understanding delegations. Exactly the same way that saying that your probability of being correct is like 0.5 doesn't mean that you have a coin and that you flip the coin and then you do the thing. It's like it's an abstraction of reality, and this is really what it is here. So the way we model delegation is you have kind of two things. One is my probability of delegating. So here it's the Q of my probability, my PI is my probability of delegating. So with probability 1 minus Q of my probability I don't delegate, which is what happened when you have like this self loop here. And then if you delegate with a probability that is parameterized by your like potential function, which is the phi function here. And phi is just a function that takes my expertise and your expertise and outputs a number, and that's the weight. And I will select you with a probability that's proportional to this weight, and proportional in that I need to still divide by all of the other weights that I assign to my other neighbors. And as I said, these are not cognitive reasoning or anything. This is just an abstraction to model delegation behaviors.
So are you assuming that the delegation is secret and simultaneous?
Yeah. Well, yeah. Yes. For you don't need to assume. Well, if you want to start thinking strategic perspectives, then whether it's secret or not will matter. If you want to check, so all of the considerations that are not purely epistemic will make that these considerations intervene. For our purposes right now, you could describe many different ways of doing it, and this still being an okay way of modeling it. But I think a good way to think about it for now is everything's secret and everything's instantaneous. And so now the question is, which delegation behaviors are such that no one gets more than a sublinear weight? which, remember, this is what gives us the final result that we're after. And so we find that we have these three classes of behaviors. The first one is this idea of upward delegation, which is probably not the most realistic, though is intuitive, I think, from like why it works. And upward delegation just means that my probability of delegating is constant. So I delegate, all of us delegate with the same probability, independently of our expertise. And then when we delegate, we pick at random someone that's strictly more expert than us. So it's like this, step function where I have weight 0 on everyone with a smaller expertise than me, and then I have weight like 1 on anyone else. Then you have the idea of confidence-based, which is that the probability of delegating decreases with your expertise, but when you delegate, you do it completely at random, irrespectively of your expertise and the other's expertise. And then you have the general continuous, which is that you can either delegate with constant probability or decreasing probability, that doesn't matter. And then when you delegate, you always delegate to someone, you delegate more often to more competent voters. And the reason why that's a little bit more interesting already is that if I'm a really high expert person, with high probability, I will always delegate downward with this scheme, and that's actually okay. So some of the nuance that we had before about there is this weird intertwinement between expertise and the weight is at play in the general continuous. Yes?
Yeah, so kind of roughly how many behaviors do not satisfy the lemma? Like kind of what portion satisfy kind of
Of all of the, I don't know, of like...
It's a bit hard to define.
Yeah, I mean, it would be, like, what we've been studying here is like basically any function QRFI. So the space is huge. And this is not exhaustive. These are some that we found interesting for a few different reasons that I'm going to outline in a second. But in terms of like how many, I don't know. And like the way that we answer part of this question, though it's not answering this question, but I think it's answering the same intuition that you're having asking it, is by running a bunch of experiments and trying to see whether what we were seeing was completely outside of this realm or not. Which, honestly, I mean, I guess we're on record, but I did a lot of the experiments thinking that the theory couldn't work because I was not, I was suspicious of this being a cogent way of modeling humans, and I was surprised. As maybe you'll be. I'll get to them in just a second, guys. Yes.
Yeah, so I'm trying to like aftershock like how people choose who to get their opinions from. Like, did you guys take a look at sort of the people with less competence being less likely to be delegating their votes, like sort of like the opposite trend of the really blue with the line
Yeah.
up? Did you guys look at that at all?
Yeah. Can you hold on that thought? Because I think, but if I don't cover it, remind me at the end, because I think it's all of these questions about the applicability and also, this is even being generous to how delegations could be, but also, is it the case that confidence trumps expertise in some cases, are questions that we've looked into in the empirical setup. And I want to get back to this particular point in the experiments side, which is coming in a second.
So could you explain why in the general continuous case, if you delegate with constant probability and you delegate more often to more competent, that you wouldn't get a concentration of the around delegation to the most competent voter? Like I could set up a function, a green function, with a constant blue, so that everyone just ends up delegating to the most competent person, and then you violate the or smaller than requirement.
So in the exactly what is required for phi is that it's continuous in its second coordinate, and it's increasing in its second coordinate. So phi is going to be, phi of x, y is going to be continuously increasing in y. So you couldn't have a case where everyone just delegates to the best person and no one delegates to the others. You have like a continuous weight. So no one has weight 0 is one aspect of the answer. And the other aspect of the answer is that by having people not delegating with constant probability, you also basically create sinks, and you can create sufficiently many sinks for concentration not to happen. But I think, to your intuition, the reason why general continuous is more interesting than the others is, in the other it's a bit more clear why things go well, is that here you have a tension between some people potentially could have a lot, but also these people could be the one that delegate to people less expert than them. So this is why this one is much more interesting from like a theoretical perspective, why it's actually satisfying our benchmark.
I see. So the problem, okay. Right. Okay.
And so what I want to do, okay, bad time management already, is I want to give you a sense of the proofs, because I think I found them beautiful in a way, but I want to give you a high-level idea of how we go through them, and then I want to go into the experiment as I think more relevant to some of the questions you were asking. So maybe I'll skip a bit faster than I anticipated to the proofs, but please get back to them in the question. And I'll show you the proof for the upward delegation one, because we also proved something that we couldn't find in the literature about polyarine processes. So, but it's the same high-level idea is going to be true later on. And the high-level idea is that we can see all of these delegation processes as basically being close to, in the case of upward delegation, exactly well-known processes, well-known like random graph processes. And the way we can see it is, let's say that we only have 3 people, the blue, the yellow, and the red, and they are ranked by their expertise. And then you look at the graph that you got from instantaneous delegations. But instead of seeing it as this one hop thing, you can actually decompose it by looking at what happens when every agent, one after the other, enters into the arena. And so first, the blue agent comes in, and that's the most expert person. In the upward delegation, also remember, you delegate with constant probability, and you only delegate to people more expert than you. So this person doesn't have anyone more expert than them, and then they're first. Then you look at the second most expert person, and either they attach with probability p, which is the probability that they delegate, and they don't attach with probability 1 minus p, which is the probability that they don't delegate. Then the red person comes in and either attaches with probability p over 2, or attaches to the yellow person with probability p over 2 and attaches to the blue person with probability p over 2. From our perspective, it doesn't matter, because in both cases, the blue agent ends up with a weight 3. Or they don't attach, which happens with probability 1 minus p. And then up, same, doesn't attach with probability 1 minus p, and attaches either to the yellow or the blue with probability p over 2, p over 2. And, again, some of them are, for our purpose, completely isomorphic, because we don't really, care how it looks like past the top node. An equivalent way of looking at this problem is thinking of this in the context of having bowls and bins, where we can look at the first instance where just the first person arrived and create a bin, and then the second person arrived and creates another bin, and then the third person arrives and creates a third bin. The second line could be created by the first person arrived and creates a bin, and then the second person arrives and creates another bin, and the third person chooses to go in one of the existing bins. So it's really a build and born problem, except that everyone has a probability of creating a new bin, which is known as infinite polyarine. Like polyarine is the traditional urn problem, and the infinite is just that you can always create another urn. And we can reconstruct all of them similarly. I'm going a bit faster on them, but I think you got the principle. And so we can really see this as in the bin problem, it's like this infinite polyarine. In the graph literature, it's a preferential attachment model. It's really the same idea, where you attach with people with a probability proportional to their degree, with a probability of creating a new component. Is the equivalent process in the like random graph or like preferential attachment model vocabulary. And so now that we have this kind of formulation, it might become much clearer how we get to prove that no one has more than a maximum that the max weight is sublinear. And kind of the intuitive way to look at it is that let's call U and K the size of the K's component, or the K bin at time n. And what we want to show is that the max size, so the size of the maximal urn, is sublinear with high probability. So the probability that its size is sublinear is diminishing with n. And the way we can think about this is really by just looking at the urn dynamic. So if you condition on knowing what happened at times n minus 1, it's super easy to know what's happening at times n, because basically either it stays the same, or it adds or you add 1. And the probability that it stays the same is the probability that you add 1 is the weight of your urn at time n minus 1 divided by everyone, which is the idea that you're going to attach to an existing urn with a probability that is proportional to the existing to the weight of this urn. And so if you look at this, then you can just think of something like the law of total expectation is you just have like a recursive expression for your expected value, the expected size of your urn. By just if you look at the expectation of this thing and you take the expectation of the expectation, it's Tower property. It has different names in different places, but it's very straightforward like probability concept here. And the way you can think about it is when I look at the probability that the max urn is greater than some number, this is the same as the probability that at least one urn is greater than that number, which is going to be upper bounded by the sum of the probability that either of these urn is greater than that number, which then you could hope to actually bound with Markov inequality using the expression that we have for the expectation here. The small issue is that if you look at the closed form, you have a closed form of the expectation that depends on like gamma functions. The rate at which it decreases is too slow for the series to actually be bounded and like be a little low of 1. What I mean by this is if you look at the sum over all of the ends of the expectation that is the term that you get is through Markov inequality, this series won't be a little low of 1. So what we need to do, and this is the step I'll go more quickly over, but we can talk about it later, is that we break the system in two, where first we look at the sublinear number of components, which is the idea that the components that should be large are the first one going in. Like it's very unlikely that the least expert person is like, it has like a lot of weight. So first we look at the first one that are likely to be big, and we just use this, and for that purpose, the expected value is small enough that we can actually bound the probability that one of the first components is too large, and this works well. And then we separate and we look at the tail ones as a separate process, where I don't know if the drawing will make the intuition work for you, but this is what I was telling you when I was telling you that we look at the bin process. And now if we have like a fourth person coming in, the fourth person create their own bin, and then we continue the process like this. When we look at them at the end, actually what we can do, it's sufficient to just look at two bins, the one with everyone and the one with just the new person. So you just create, now you have a two bin problem, one with everyone and the other one with just your person, and what you'd care about is how many people can come into the green person's bin. And so you just have two bins, and we exactly know how this behaves. We know that the fraction of the people in the second bin is just following a binomial beta distribution. There's a little trick, which is that the parameters of your beta distribution actually depends on m, so you need to do some careful work about the rate of convergence of the process, but like that's much more standard like poly-iron process type things. We can get back to it, but I actually want to make sure that I cover the experiments, and we're already very close to time. Yes, of course.
I mean, this feels a lot like a variation on like these Chinese restaurant processes or the Indian. I mean, the Chinese restaurant process in particular, but it has a different preferential attachment model than the poly-iron. There was a time in the world when everyone was analyzing this process all the time. I don't know if any of that machinery was how we did this in first place.
No, so we ended up. So the way to think of, I think, and I don't know exactly the results you're referring to in the. I don't know which ones were more popular in what you were mentioning, but one of the things that we reproved with looking at this expectation, the recursive formula for the expectation, is just that with the expectation is going to get very, very small as n increases. The thing that we couldn't find in the literature was that these in-expectation results carry with high probability result. So we just proved that the second part is what we proved that's new, but the rest is things that did completely exist before in the literature, and that we did I think rewrite the whole thing in the paper, but it's definitely the whole first part are things that are completely known already from that. And so basically for the other processes, it's the same idea where we relate our delegation graph to a well-known random graph. And we just compare them, and we show that these graphs are sufficiently bounded for our purposes. So the takeaways of this part is that we provide a framework to analyze the networks dynamics of the delegations. We identify the classes of delegations. So to your question, we don't have I can't quantify how many are working and how many are not. Where liquid democracy works well, and we prove this new high probability bound on the size of the largest component of the infinite poly-iron process. Now I want to get into the experiments, and I'll just ask you to remember the continuous general, which was one where my probability of delegating decreases with my expertise, and the way that I put increases, I delegate more often to more competent voters. So this was just like the third mechanism. I just want you to like have this in your mind as we move on to the experiments, which was asking the exact same question, but from a practical perspective. So running experiments, and what I mean by experiments is we worked with a bunch of groups of people who had existing social networks, otherwise we can't do liquid democracy, and we asked them to make decisions and either vote themselves or delegate. And so it would work like this. You would have, for instance, English idiom as being like a topic, and then you would be like do you want to vote or delegate to appear? And then if you vote yourself, you just go into the questions and you answer a bunch of questions. So you have like M questions. And so you delegate before you actually see the questions. You delegate at the level of a topic. And then here you have historical monuments. And then maybe you delegate to appear. And then you pick someone from your group. This is the experiment. Super simple. And so the way it would work from like a diagram perspective is that during the first stage, you do exactly what I showed you, which is, you look at a task and then you either vote or delegate your vote after all of the like, informed consent and like giving your name. And then you have a second stage in which every single topic you delegated, I throw them back and I ask you answer all of these questions that are related to the topics that you delegated, but you don't know why you're answering these questions. And so the reason why I'm showing you this, because with the one same design and this one same experiment, we could reconstruct both worlds, the one where everyone voted and the one where you had liquid democracy happening. And because people don't see the questions when they delegate, we don't think that it primed them by doing the second stage second.
Also, this gives you PI.
Yeah, exactly. So next slide. First numbers, so we have 12 experiments, almost 300 participants, and like 11,000 votes. But this gives us the PI. So if I look here at, this is one of the instances of the delegation graph that we have. The number is your PI, is your expertise, and the arrow is the delegation. And we get the PI because we ask them to answer all of the questions, even if they delegated. And the way we estimate the PI, we do something a tiny bit more robust than just looking at the average number of questions that were answered, because you can have some heterogeneity in the different complexities of the question. So we use a very well-known framework from 2000s called item response theory, which is just saying that if you look at all of the answers that someone gave, because maybe there is some complexity in the questions, you actually learn the expertise by taking into account both the complexity and the question and people's expertise. So you parameterize the outcome as just saying that it depends both on the PI and the theta j, or theta q here, which is the complexity of your question, and you do maximum likelihood type of estimations here to just recover your PI. And they're actually super similar. The results don't change if you do this, but this is just a more rigorous way of doing the analysis. Then we go into estimating the Q, and we do this this is simple logistic regression, where we have the outcome and we have the expertise. So we run a logistic regression, and we find that the probability that you delegate, which is this Q of PI, has this decreasing relationship with a PI. And you see that, so the parameter that matters in the logistic regression is this minus 2.24, and you run the wild test on it to get the p-value. That's the one I showed on the right. Yes?
When you ran this experiment, what information did each person have about who they were delegating to?
In the experiment, nothing. So we could work with you and make you work with this experiment. So I don't know if you talk a bunch about historical monuments. It's information that's tacit information that you have about one another based on the interactions that you have, and that's the only thing that you can rely on when you delegate. Yes.
Did all the questions say to a trusted peer, like you did in that screenshot?
Yes.
Or did it sometimes just say delegate?
No, that was always the question that was asked. It was always in this, how it was phrased here. And then we reconstruct the phi, which there's also a lot of fun things on how you actually reconstruct the phi, because it's harder. One thing you could do is think of graphen types of thing if you wanted to keep the continuous nature of the data. We actually do something that makes the analysis easier, though I'm sure there would be other ways of doing it. But so the way we do it is, this is your graph. You have all of your PIs, and what we do is we bucket the PIs. So we cluster the PIs, and we use a bunch of different heuristics. We make sure that this is robust to the number of the buckets and the different heuristics for clustering and different granularity, and this is all the case. I think the results I'm presenting here are for just k-mean clustering. So you cluster them, so now you don't have the PI, you have just a color of PI, which is your bucket. And then what you care about is to estimate this phi of x and y for a fixed x. So I look at the probability that a person of type 1 delegate to the people of type 2, 3, 4, and 1, which are all of the possible people that they have in the network. And we kind of collapse the entire network onto just this small screenshot where you look at the people with fixed expertise and you see the probability with which you delegate to them. And the reason why this is working well is because now the probability that I delegate to person 2 depends on both the phi of 2 that I'm trying to estimate, but also on the number of people of type 2 that there is in my graph. And so this is exactly, I don't know if you're seeing this coming, but this is exactly a multinomial trial. It's exactly like I'm throwing a dice, and each face of my dice has a different probability of appearing. And this probability is what I'm estimating, except that I'm not estimating that exactly, because it's like that. What I'm estimating is the number of people which I have times the parameter I'm estimating, which is what we have all the way there. But it's exactly a multinomial trial, so like same, you can do like maximum likelihood estimation in this. You have a closed form for that, and you actually get a closed form estimate for the phi. So you can reconstruct the phi, and then you can see that your phi follows the following pattern. So here you have your 4 clusters, and you see that you're just more likely to delegate to someone that's higher than you. And then to answer your question earlier, no one has weight 0, so we don't have like any pathological or like discontinuous pattern happening here. And then so the statistical test that we do here is we have the phi's and we have the pi's, and we run a rank correlation test, which looks at the ranking of the pi's versus the ranking of the phi's. So bottom line, and I think to one of the questions that was asked earlier, I was actually surprised to see that we would see something that was close to what we had found in theory, which is that the summary of our the Q and the phi actually fall into the continuous general perspective of what I was saying. Something that might be of interest is liquid democracy actually doing better? I mean, our theory should say so, but just to check it, that's the case. If you look at the average improvement of liquid over direct, it's significant. It's only 4% across all of the categories, which you can think of it's only 4%, but then if you do like millions of experiments or like real world decisions, then it's like a 4% increase over a million questions can actually be significant. But also you have a ton of heterogeneity. Like some questions we have a 12% increase, and some questions we have no increase. And here, so the takeaways is like this was the first. There's a lot of theoretical research now on liquid democracy, and it was never tested, and this is what we did. But what I found most interesting from like a kind of epistemological perspective of like why do we do social choice theory was the alignment between the theory and the practice. And I won't bother you with my philosophy, and so I'm just gonna go to the last slide. Thank you.
Thank you. We only have time for like one more question. We had a lot of questions. One last one.
I guess I'll ask one.
Yes.
So you had multiple questions per category.
Yes.
How did you define correctness?
Oh, so the questions it was like a right or wrong type of things. Like for instance, historical monuments, I would show a monument and I would say, is it in like, is it in France or in the United States?
Yeah, okay, but they might end up on average correct on some questions and incorrect on others in that category, and the person delegated for all the questions.
Yes, so the delegate for all the questions, and what we need for the experiment is to define the expertise. And so we use, if you were correct like 50% of the time, then this parameterizes your expertise.
Okay.
Which is what matters when we formalize the theory. Your phi depends on the relative expertise.
But when you made that final plot, you just averaged over all the questions in that category?
Yes, that's a great question. We in one of the, I think here we average over all of the questions. We also test whether liquid was right and direct was right in all of the cases, and do this average, and both results are super similar. I think this one is actually over all of the questions, but I think that would answer more precisely I think what you're saying is saying, was liquid correct in this group, that group, that group, that group, compared to whether direct was correct in all of these groups, and looking at that average per question. But yeah, that's a really good point. Thank you for saying this.
Very good.
So obviously when you're talking about these types of like voting systems, the thing that comes to mind, at least for me, is politics. Is this applicable in a world where there aren't necessarily correct answers, and what you're going for is the most amount of people as satisfied as possible with the outcome?
Yeah, thank you very much. And that was related to your question, and so sad that my I need to be better in time management. So that it's a great question. That's the reason why I worked on this, was to think about real world impact. So I would decompose the answer in two very quickly. First, I think of most political decisions as being decomposable on like a right, wrong, and a value aspect. So I kind of see this like you have these two dimensions, and then every question is like some weight on the one and some weight on the other. Like I think during COVID, maybe having a like committee of experts elected with something like this, to me would have made sense, at least conceptually. In that these are questions on which they're super hard, we don't know the answer, but there is like a standard of like this is going to be better for our health than something else. Some other questions are so value based that this would be a terrible model. So there's really this thing of, and in fact, I've worked with applications with also companies, and one of the best places where I've worked on this particular application is we designed a what we call liquid forecasting, which is using liquid democracy in prediction markets, because this is a place where this is not a model for reality, it's like the reality. But then the second aspect is, if we were to think about where to do this in reality, I'm not saying we should just throw out the Congress and change it with liquid representatives. That would be probably a terrible idea for a lot of practical reasons, also one of which that you were mentioning with cycles. But one thing I've been thinking about is, if you heard of this idea of sortition and citizen assemblies, it's a process where people are selected at random to make some recommendation for policies, and before this happens, you have a committee of experts that's selected to teach the citizens about an issue. And these questions about when you have expertise and you don't know how to sample this expertise, it's one of the places where I love to work with some of the people working on citizen assemblies to think, could you source your experts using something like this? Which is, it's like, there's a lot of ideas, like small world work is really linked on this idea that we are super well connected and we know so much about each other, and this is such a rich source of information that we're never using, not in politics, but neither in, I also worked on this for my department. We did an experiment with the department. It's another place where, that would be useful.
Thank you very much for this talk. Thank you all for coming.